All right, so now we're going to formulate another Cauchy criterion for integrability, and so I want to kind of go back to the thing I was just saying at the end of the previous video, which was that we can kind of think of P. So in the previous Cauchy criterion, we think of P as a parameter controlling convergence, right? But P is like, as a parameter, it's not really as nice as something like N, right? Because P, like, so, but P is not as simple, since there are infinitely many ways, infinitely many ways to make P finer, right? So the idea is that it's like, if you want to force the convergence process to continue, you want to keep adding points to P, right? So, i.e., add points to P, right? In a sequence, if you want to make the convergence happen, you just make N increase, right? So it's like N can go to N plus 1, go to N plus 2, and so on. But P can go to like P union, you know, X, or like P union Y, you know, P union Z, or whatever. There are all sorts of like points that you could add to P, and then of course, you know, you can keep adding X X prime, I don't know, P union X, X double prime, who knows, right? And then like you could just keep, so this is like very different, right? And it would be nice, so this is like for sequences, for integrals. Right, for N, there's only one way to like make it increase, right? But with a partition, you can keep adding points however you want. And the other thing is that like just adding more points does not force U of FP or L of FP to converge to the integral from A to B of F. Okay, because what you could do is like, you know, just very roughly, you could have like, let's say this is A, this is B, you know, this is like T1, and then, okay, so it's like, okay, maybe, so I'm just going to keep adding points, and I'm going to hope that the upper and lower sums converge to the correct values, right? But then maybe I add T2 here, and then maybe I add, you know, T3 here, then maybe I add T4 here, and I keep inserting T k plus 1 in between Tk and B. So then the error in the first, you know, n minus 1 intervals never goes away, right? So the approximation never gets better on these intervals over here because I never add in more points over here, right? So how do we prevent this from happening? Well, force the maximum of the tk minus 1 to go to 0. So the points of P become arbitrarily dense in AB, right? To this end, we define the mesh of P to be just the maximum of tk minus 1 for k equals 1 up to n. Okay, so it's the maximum width of a rectangle in U of FP or L of FP. Right. So by forcing the maximum width of a rectangle to go to 0, that forces the partition P to become the approximations to become very good, because P becomes very fine on the entire interval, right? So now the mesh of the partition, you can actually treat it as like a one-dimensional parameter that controls the convergence. So, so it turns out mesh of P can be used to control the convergence. So this is the statement, this is the theorem 32.7. So a bounded function f on B is integrable if and only if for each epsilon greater than 0, there exists a delta greater than 0 such that for all partitions P of AB with mesh of P less than delta, we have U of FP minus L of FP is less than epsilon. Okay? So, right, so this is kind of like an epsilon-delta Cauchy criterion of integrability, because basically now we just have this one parameter delta, which we can choose based on epsilon to force these approximations to be arbitrarily close to each other and therefore arbitrarily close to the value of the integral, right? So how do we prove this? Well, clearly, if such delta exists for any epsilon greater than 0, then f, the integral exists by the previous Cauchy criterion, right? Because in the previous Cauchy criterion, it was just saying if there exists a partition for any epsilon that makes this be true, right? But if we can choose a delta such that all partitions with mesh P less than delta have this true, then obviously some partition exists for which this is true, right? So that direction is kind of trivial. So suppose the integral from a to b of f exists and let epsilon be greater than 0. So our strategy here, pick a sort of reference point such that u of f p naught minus L of f p naught is less than epsilon over 2. Oops. And then pick delta such that if mesh p is less than delta, then u of f p minus u of f p naught, I guess. Let me is less than epsilon over 4, and L of f p naught minus L of f p is less than epsilon over 4. Okay, so then u of f p minus L of f p is less than u of f p naught minus L of f p naught, u of f p naught plus epsilon over 4 minus L of f p naught minus epsilon over 4. So then u of f, so this is in turn less than epsilon over 2 plus epsilon over 2, which is epsilon. Okay. Because u of f p naught minus L of f p naught is less than epsilon over 2, sorry, then, so there's that. Okay. It's then like, you know, so this u of f p naught minus L of f p naught is less than epsilon over 2, then these epsilon over 4s combine to give a different, another epsilon over 2, and then those add up to be epsilon. So overall, so the strategy, so really it's just picking this delta so that whenever mesh p is less than delta, then these things are true. That's kind of the difficult part. Okay. So the idea is that it's like, okay, given p, p naught and p, we can compare we can compare them by looking at q equals p union p naught, right? So okay, sorry, I had to double check something in the notes, but basically, okay, if we just look, let's just look at how far apart the lower sums for p and q can be, basically, okay? In terms of the mesh, all right, so let's try to relate it to the mesh, because then that'll tell us how we have to choose the mesh. Okay, so let's look at like the lower sums, for example. So if q is the union here, then the lower sum with q should be bigger than the lower sum with p. So let's look at L of f q minus L of f p. Okay, so if q has one more element than p, then L of f q minus L of f p equals, right? It equals like basically just whatever the element. So let's say u is the extra element, right? Then it'll be like little m of right of t right t t k minus 1 u u minus tk minus 1 plus little m u tk times tk minus u minus little m of tk tk minus 1 tk times tk minus 1, right? So the picture here is that we just have this like, so this is like tk, this is sorry, this is tk minus 1, this is tk, and here's u, right? So then basically you just get these new, whatever, new minima, new infima, right? So probably one of them is the same. It doesn't really matter, right? But basically it's like this difference is bounded above by essentially, whatever the width of this entire rectangle is, like the really worst case scenario would be if these new infima were like the maximum value of all of f, and this old infimum was like the minimum value, basically. So it would be like, right, b, right, yeah, let's say like b times u minus tk minus 1 plus b times tk minus u, right? Because like basically this is, well, let me explain. I haven't defined b, but I'll explain in a second. So, and then minus like negative b times tk minus 1. This equals 2b times tk minus 1, which is tk minus 1 is the index here. Which is in turn less than or equal to 2b times the mesh of p. Okay, and b is an upper bound on f of x on the whole interval ab. Okay, so basically the idea is that it's like, okay, when you subdivide an interval like this, so like say we already had an interval tk minus 1 to tk, and then we put a new point in, right? The worst case scenario, which can't really even ever happen, but let's just say that it could. The very worst case scenario would be like the new minima you get on the smaller intervals are actually like the biggest possible value that f can achieve, whereas the old minimum was actually like the smallest possible value that f can achieve, right? Then that would result in the biggest difference between the area of the two new rectangles and the area of the old rectangle. So that's why we have b over here, and then like negative b, that's like the smallest value, right? So we end up with 2b times the mesh, right? Because tk minus 1 is less than or equal to the mesh of p, okay? So if q has m more points, then, or let's say n more points than p, then so LFQ minus LFP is less than or equal to 2m b b times the mesh of p, by the same reasoning, right? Because basically the worst case scenario would be if you added in, you know, each point into a different interval of the old partition P, then you'd incur another difference of like 2B mesh of P each time, right? So so this is what we have now. Or sorry, N, this should be N. So say P naught has M points, right? So we already fixed P naught in the very beginning, if you remember, right? We chose P naught at the beginning here, and now we're trying to choose mesh. We're trying to choose an upper bound on the mesh of P using the P naught that we chose, okay? So let's say P naught has M points. Then pick delta to be epsilon over 8mb, okay? Then for any P with mesh of P less than delta, we have that L of FQ minus L of FP is less than or equal to 2mb, sorry. Right, because P naught, if P naught has M points, then Q can have at most M more points than P does, right? Which is less than 2mb delta, which equals epsilon over 4, right? Where Q is P union P naught, right? So then since L of F P naught is less than or equal to L of F Q, just because Q, since P naught, so P naught is a subset of Q, we also have L of F P naught minus L of F P is less than epsilon over 4. And similarly, U of FP minus U of FP naught is less than epsilon over 4, right? So that's, so then U of FP minus L of FP is less than or equal to, or is, let's say, less than U of FP naught plus epsilon over 4 minus L of FP naught minus epsilon over 4 quantity here, which is less than epsilon as desired, right? This was for any P with mesh of P less than delta. Remember, right? So we chose delta, and then we said for any P with mesh P less than delta, all of this stuff is true, because we just bounded above the difference between this like finer partition Q, and then we just know that, like, you know, P or P naught is like is just like a worse approximation than that. So like it has to, L of F P naught has to be less than L of F Q, so this difference is less than epsilon over 4. Okay. So anyway, yeah, I know it's a bit of a complicated argument, and I don't know. Hopefully I was able to sort of outline some of the broader organizational ideas in the argument. But at any rate, yeah, that's the Cauchy criterion using the mesh. The Cauchy criterion for integrability using the mesh. So yeah. All right. That'll be it for this video. And then in the next video, we'll talk about Riemann integrals and Riemann sums.